Hello, hello, hello. This is Coach Ikram, and welcome to video 2 of our gas law unit. In this video, we are going to go over Dalton's Law of partial pressures, and we're also going to discuss the 4 variables that we're going to typically use in gas law calculation problems. So starting with Dalton's Law of partial pressures, this law states that in a mixture of gases, the total pressure exerted by the mixture of gases is going to be equal to the sum of the partial pressure of each gas. So the way that's going to work is defined by this equation right here. P total, that's the pressure of all of the gases in said container, is going to be equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on and so forth. So for example, in the visual right below here, we've got hydrogen gas and helium gas. Hydrogen gas has a pressure of 2.90 atmospheres. Helium gas has a pressure of 7.20 atmospheres. And over here, in our mixture of the hydrogen and helium, that pressure, if you added that together, would end up being 10.10 atmospheres. It's also defined by the little weights at the top. So you've got 2 here, 5 here, and a total of 7 here. So an example is air. Air contains nitrogen, oxygen, H2O, argon, CO2, etc. And the total air pressure is 101.3. So if you were using our equation, that'd be P total equals P1 plus P2, etc. P total would be 101.3. So you can see down here at the bottom, we've got all of the individual pressures for each gas that makes up air as we know it. And if you added those all up, it would equal 101.3. So an example is a sealed room contains a mixture of air and sulfur hexafluoride gas at total pressure of 105.4 kilopascals, which is a unit for pressure, which we'll get into in a few minutes. The air pressure in the room is 101.3 kilopascals. What is the partial pressure of the sulfur hexafluoride? So my equation is P total equals P1 plus P2. When I go ahead and fill that in, I've got my P total is 105.4 kilopascals. Pressure 1 is 101.3 kilopascals. And we're looking for pressure 2. Rearrange and solve, and pressure 2 is equal to 4.1 kilopascals. So again, it's very simple mathematics, but you do need to understand the concept behind that formula. So the 4 variables that we're going to typically use when we're talking about gases. The first one is pressure, designated by a P. Pressure is created by the molecules of gas colliding with the walls of the container. The SI unit for pressure is going to be pascals. And when we're talking about pressure, oftentimes you're going to need to convert because pressure, depending on what you're measuring it with, would be measured with a different unit. And so we use these units right down here. This is just an example. We've got kilopascals here. We've got atmospheres, millimeters of mercury, which would be, say, what a barometer would measure for pressure, and torr. So this is the equivalent. 101.3 kilopascals is equivalent to 1 atmosphere, which is equivalent to 760 millimeters of mercury, or 760 torr. So the practice problem at the bottom says, convert 1.4 atmospheres of pressure to kilopascals. And you would essentially do this with dimensional analysis. So I'm going to start with my given, which is 1.4 atmospheres. And I'm going to do dimensional analysis. So every 1 atmosphere is equivalent to 101.3 kilopascals. I solved that out, and I got 141.82. If you talk about significant figures, it would end up being 140 kilopascals. And that's how you convert between pressure units. The second variable is temperature. designated with a T, and it's going to be a measurement of the kinetic energy of the gas particles, and it's directly proportional to the kinetic energy. So the higher your temperature, the higher the kinetic energy of that gas. So in the little diagram here on the left, we add heat to our gas, and the gas has higher kinetic energy, therefore they're going to move faster. The SI unit for temperature is Kelvin. All the calculations in this unit are going to be in Kelvin. That doesn't mean that you're not going to come across some Celsius in the problem, but that means that you're going to have to convert before you do any math with it. So to convert from Celsius, we're going to use this equation right here. Kelvin is equal to degrees Celsius plus 273. Standard temperature is going to be 273 Kelvin or 0 degrees Celsius. 0 Kelvin is going to be called absolute zero, and that's the temperature at which the motion of particles theoretically stops. Because remember, at most temperatures, even if it's a solid, the particles are still moving. So we've got this practice problem down at the end, at the bottom. It says convert 33 degrees Celsius to Kelvin. And note that we don't say degrees Kelvin, we just simply say Kelvin. That's just a slight notation to be aware of. So I'm going to convert 33 Celsius to Kelvin. So Kelvin equals degrees Celsius plus 273. So we've got, I'm going to come up here, 33 plus 273, and I get 306 Kelvin. The third variable is volume, designated with a V. Volume is essentially a space. It is the 3D space that's going to be enclosed by the container's walls. So it could be whatever container that you're dealing with, rigid, flexible. The SI unit for volume is going to be liters, which we've used before. And again, a note that you already know, an STP, there are 22.4 liters of a gas in 1 mole of that gas. And that applies to any gas at STP. The fourth variable is moles, which is notated with an M. That's an important distinction. Don't notate it with an M, because remember, M is meters. The amount of gas present in moles. So it's essentially like how much of the gas you have. If the amount is given in grams, you're always going to convert it to moles. Don't leave it in grams because moles is what we're going to use. It's the standard at STP. So for example, in this balloon in the diagram, we have 1 mole of oxygen gas, which you know occupies 22.4 liters if it's at STP, and is going to have a mass of 32 grams, which you should know because it's O2. And the balloon has a diameter of 35 centimeters. And STP. STP is standard temperature and pressure. We talked about this a little bit before. The temperature for STP is going to be 0 degrees Celsius or 273 Kelvin, and the pressure is going to be 101.3 kilopascals, 1 atmosphere, 760 millimeters of mercury, or 764. And that is the last slide of the video. So if you could go ahead, make sure you rewatch, take good notes, and come in with questions. Thanks.